Okay, Algebra 2, we're transitioning now kind of into the middle of Chapter 4. So in 4.1 and 4.2, we were really learning just how to graph quadratic functions. Now we're moving towards the second big thing that we're going to do in almost every chapter this year, learning how to solve different types of equations. So solving quadratic equations is what we're going to be focusing on pretty much from here on out in Chapter 4. But right now, we've got to do a little Mr. Miyagi wax on, wax off kind of prerequisite skill before we can get into actually solving those equations. And what we're working on in 4.4 is reviewing a skill that you guys should have learned pretty well back in Algebra 1, factoring quadratic expressions. Although some of the ones I've given you here are even more complex than quadratic, but that's okay. So let's have a quick review of an entire chapter that you guys did in Algebra 1. The first thing we're going to talk about is called monomial factoring, but also the phrase GCF right here might be close to mind right here, greatest common factor. The first thing we want to look for in any type of factoring problem where we're trying to break something down into the product of multiple things being multiplied together is pulling out a greatest common factor. So let's take a look at what we're dealing with here in example A. You've been given here a binomial expression that's written in what we call expanded form. And you can tell it's expanded form because the expression is written in terms of either addition or subtraction. There's a big minus sign here in the middle, and we've got one term right over here on the left, 15x cubed, minus a second term, 35x squared. So that's in expanded form. Our job is to get it in factored form, and I'll explain that once we see one written out that way. So we begin by looking for the greatest common factor of these two terms that we have here in black. And we can look at that both in terms of the numerical components, the coefficients, and also the variables. So here we go. The first term has a coefficient of 15. The second term has a coefficient of 35. Technically, that's negative 35, but that doesn't really matter here. All right, guys, this is going to test your knowledge of basic multiplication facts, which some of you guys have been skirting on for the last several years. So here we go. The biggest number that goes into both a 15 and a 35, I started you off with one that I hope was easy, is going to be a 5. That's what we're going to pull out in front. And then we're going to look at the variable components. X cubed is really x times x times x, and then over here x squared is x times x. And what we want to do is pull out all of the x's, or the variable factors, that these two terms have in common. Common means they both possess them. So the question is, how many x's do both of these two terms possess? They both have 2. One of them has 3, but not the other one. So we can pull out 2 x's. So 5x squared, everybody, right there is our greatest common factor. That is what we pull out in front, and then we start a set of parentheses. And now it effectively becomes a division problem, although I think most of you guys won't like to look at it that way. But this first term had a 15, and we pulled out a 5. 15 divided by 5 leaves us with 3. And there were 3 x's on the first term. We pulled out 2 of them. 3 minus 2, we are left with 1 x from that first term. Then, whatever sign this is, a plus or a minus, gets written right over here now. And then we go to the second term. There was a 35. We divided out the 5. So that leaves us with a new coefficient of 7. And in terms of variables, there were 2 x's there. We pulled both of those x's out in front, so there are no x's left. So then we close the parenthesis, and what we have right here, everybody, is our factored expression here that is equal to, let's not lose sight of that significance here, equal to the original expression. All right, but we now have it in what's called factored form. So let me write that out for us so that's a little bit easier to see. So what we had on the left we said was expanded form, written in terms of addition or subtraction. This expression is in what we call factored form. And the word factor always implies multiplication. Now that dot looks silly by itself, but this is 5x squared multiplied by the binomial 3x minus 7. Now, what I'm hoping is clear, and we'll illustrate this real quick, we have not changed the value of this expression at all. Just for fun, and I picked some big numbers here, but okay, I'm going to choose a relatively small value for x, like x equals 2. Let's plug that into what we have right here, guys. I just want to prove to you that this works. The original expression is 15 times, that would be a 2 cubed, minus 35 times 2 squared. All right, guys, 2 cubed, 2 times 2 times 2 is 8. 15 times 8 is 120. Minus 2 squared is 4. 4 times 35, I believe, is 140. And 120 minus 140 is negative 20. So that's the value of the original expression when we let x equal 2. But this equal sign should come right down here, and we now should get the exact same value from this expression when x is equal to 2. So that's a 5 times 2 squared, and then in parentheses, 3 times another 2 minus 7. Let's see what that gets us here. That 2 squared is 4, and 4 times 5 is going to be 20. And that is getting multiplied by, okay, 3 times 2 is 6. 6 minus 7 is negative 1. Well, sure enough, 20 times negative 1 is negative 20. We got the same value from each of the two expressions, the expanded form on the left and the factored form on the right, when x was equal to 2. And I promise you that will happen no matter what x value you were to choose. So what we've done is we've converted from expanded form into factored form. Now the benefits to that are pretty wide and varied here, but they're really going to have to wait until later on in this chapter. I don't want to bore you guys with it right now to see why that's a benefit then. Okay, so that's called monomial factoring. You pull out your GCF in front, and then with what's left over in parentheses, that's the second factor. Okay, hopefully that rings a bell, guys. Let's do one that's a little bit more complicated than that. This one is a trinomial expression with multiple variables in it. Okay, we can handle this. So let's take a look. We are looking at coefficients of 16, 24, and 40. So we're looking for the biggest number that goes into all of those. Here's the way I would approach this. Start with the smallest number, which is 16. The best case scenario is that 16 would actually divide evenly into these numbers here, but that doesn't happen here in this case, guys. 16 doesn't go evenly into 24 or 40 for that matter. So then start thinking about big factors that go into 16, and the best thing you should always think of is half of that number right there. Half of 16 is 8, and now start thinking, does 8 work here? Yes, it does. And does 8 work here? Yes, it does. Then 8 is the greatest common factor of 16, 24, and 40. Now let's start thinking about variables. We have, let's count them, 3x's, 5x's, 7x's. We want to take out the biggest number that we can, but what they all have in common is the lowest exponent out of those three. They all contain 3x's. All right, the 5 and the 7, they don't all have that many. And now you'll notice there are y's up here as well, but the first term doesn't contain any y's at all. That means that you cannot pull any y's out from this entire trinomial expression, and that 8x cubed is your greatest common factor. Okay, so we pull out the GCF, and then we start a set of parentheses with what's left over. So here goes. 16 divided by that 8 that we pulled out is a 2. And there were 3 x's. We pulled all 3 of them out, so there are no x's left from this first term. Moving on, I got a minus sign right here, so I'll bring that down. The 24 gets divided by the 8, and that leaves us with a 3. There were 5 x's here. We pulled out 3 of them. That leaves us with 2 x's left over. There were 2 y's. We didn't pull out any of them, so y squared is what stays right there. And then a plus sign here between the second and the third terms, and here we go. 40 divided by 8 is a 5. There were 7 x's. We pulled out 3 of them. That leaves us 4, so 5x to the 4th. There were 3 y's, and again, we didn't pull any of them out, so y cubed is what's left over. And that, everybody, is our factored expression. And that's the answer to example 1b. One thing I should have said on the previous example, if you now have an inclination to do something here, because your instincts kind of tell you, I get it, a monomial multiplied by a polynomial is when we normally would do the distributive property. But the distributive property is the exact opposite of what we're trying to do here. The distributive property starts you here in a factored expression. And if you guys notice, if I distribute the 8x cubed back in there, we get right back to this line over here. So that would just be undoing all the progress that we made. But we should realize that distributing and monomial factoring are two opposite. They're kind of inverse operations. Distributing takes you from factored form into expanded form, and factoring goes the opposite direction, from expanded form down here into factored form. Okay, so those two examples were just meant to refresh your memory on GCF monomial factoring, but this, everybody, is what we're really going to focus on here within section 4.4. That should have been an A because I restarted here. Number 2, quadratic trinomial factoring, otherwise known as reverse FOIL. Now, I better take just a second here, guys, and refresh everybody's memory on what this acronym right here, FOIL, means. It is a way to help you multiply two binomial expressions. Let me give you an example here. If we started off with something like x plus 8, and we were going to multiply that by x minus 3, FOIL is a way to help us do that. Now, I know some of you guys in Algebra 1 might have had teachers who didn't use this phrase here, and you learned something called the double distributive property. FOIL is the double distributive property. You were taught correctly. This is just one way to remember it. So what FOIL stands for, guys, is this little acronym right here. First, outer, inner, and then last. It's reminding you to multiply 4 sets of numbers right here in order to get the expanded form of this currently factored expression. So let's take a look at what that means. The F in FOIL stands for first. We're going to multiply the first term of this binomial times the first term of this binomial. And x times x is x squared. Okay, that's the first. The O stands for outer. We're going to multiply the two outermost terms here. This term, the x is on the outside, and then this 3 right here. These are the two outside terms. So we multiply those. X times, be careful now, that's actually a negative 3, is going to get us negative 3x. And there's the O of FOIL. The I stands for inner. This term times this term. 8 times x is going to give us a plus 8x. Got it? And then the L stands for last. This term here times this term here. And be careful, that's an 8 times a negative 3, which is actually negative 24. Now, most of the time that we do FOIL, there's a little bit of simplifying that can be done in your final answer, and that is usually those two terms in the middle, which end up being like terms and can be combined. So this is going to be an x squared. Minus 3x plus 8x is a plus 5x, and a minus 24. So we went from factored form here to expanded form over here on the right. That's what FOIL looks like, all right? That's how we take two binomials and multiply them together. So now what we're going to do here is work in the exact opposite direction, reverse FOIL. So here's the way this works. The first thing we would always want to do is look for a greatest common factor and see if there's anything we can pull out front. But if you look, there is no number other than 1, which is no help to us right here. There's no number that you can pull out from all 3 of those terms. 1, 10, and 21, nope, no common factor. And there's no x you can pull out because this last term doesn't have any variables there at all. So there is no GCF, but it still was a good thing to think about. Then here's the way this works, guys. We try to write this now as the product of two binomials. So I'm going to set it up this way. And we go term by term. How do we break down an x squared? What times what will multiply to give us x squared? That's going to be an x times x. Okay, that takes care of that. Now what we're going to do is we're going to focus on the signs. Right here, there's either a plus or a minus sign, and the same thing happens right here, either a plus or a minus, and we don't know which it is yet. So here's how we read this, guys. We look at that sign right there, and since that sign is a plus, that tells us that our two signs are going to be the same sign. Either they're both positive or they're both negative. Because when I multiply this number times this number, it's got to give me a positive 21. And the only way to do that is two positives or two negatives. Then we look over here at this sign, and because that the first sign we looked at said they were the same, this tells us the signs are going to be both positive. So I'm going to put a plus right here and a plus here. Don't worry, I'm going to show you more examples in a minute of what it looks like when these signs are something different. And lastly, we need two integer values, probably integers here, two constants, that multiply to positive 21, and then they need to add up to 10 in the middle. So there aren't too many factor pairs that give you 21. The first and probably only one that comes to mind would be 7 and 3, and sure enough, 7 and 3 add up to 10. So you can put them in whatever order you want, but I'm going to write x plus 7 and x plus 3. And everybody, I am pretty confident that that's my answer. I'm going to go ahead and box it up, but just for fun, I'm going to check that with FOIL to make sure we got it right. First product, x times x is x squared. Outer product, x times 3 is a plus 3x. Inner product, 7 times x is a plus 7x. And the last product, here times here, 7 times 3 is 21. Well, sure enough, those two terms combine to a plus 10x, and that is exactly the same as the original expression we started with, x squared plus 10x plus 21. So now we know for certain that we factored this one correctly, and our answer here is x plus 7 times x plus 3. Okay, that's what reverse FOIL kind of looks like. So let's see. We did that already. All right, so let's take a look at a second example now. And again, instead of a D, that should have really been example B. Sorry about that. Here we go. 3x squared minus 6x minus 45. Now, the first thing I said we should look at on the last problem was a greatest common factor. Now, there wasn't one there, but it's still a good idea. So let's look for a GCF here. Now the plot thickens. 3, 6, and 45. Look for the smallest number first, which is 3, and notice the 3 goes into 6, and it also goes into 45. So I'm going to pull that 3 out. Now there's 2 x's, 1 x, no x's. We can't pull any x's out, guys, because all 3 terms don't contain an x. So 3 is it for your GCF. And that leaves us then with, when we divide out the 3, x squared minus 6 divided by 3 is 2x, and then minus 45 divided by 3 is 15. Now, it's going to be tempting for some of you guys to box this up and say, okay, I factored it and I'm done. But when the directions say factor, it always means factor completely. And we have factored this expression a little bit, but we want it factored all the way. Now, what's important here, guys? This 3 never goes away. So my next line begins with that 3, but now I'm going to focus on what we just did on the last problem. We have a quadratic trinomial, so I'm going to try to split that up into the product of two binomials. Here we go. How do we break down x squared? That is going to be x times x. Now we focus on the signs, and I'm looking right here. Now let me go back 2 slides. That 21 was positive, and that told us that our two signs here were going to be the same. Well, that didn't happen here. If it's a minus, that tells you that the signs here are going to be different. And there's only one way to do that, guys. If the signs are not the same, then one of them has to be a plus and the other one has to be a negative. That's the only way to multiply these two constants together to get negative 15. One's got to be positive and one's got to be negative. And now we're looking for two numbers here that multiply to that negative 15 and they're going to combine to a negative 2. So factor pairs for 15, it's either 3 and 5 or it's 1 and 15. 3 and 5 have a difference of 2. And this is going to be a difference because the signs are different. That means that to combine these two numbers, we're actually going to subtract their values. And when the signs are different, whatever sign you have right here, which in this case is negative, that is where the larger of these two numbers is going to follow. 5 is my bigger number, so that goes with the minus sign right here. So that's going to be an x minus 5, and then the smaller number, 3, is going to go right there. Now, if this had been, don't change this, guys, if this had been a plus right here, then it would have been plus 5 and minus 3. Okay, so I think we got it right. In fact, I know we do, so let's box it up. But real quick, if we wanted to check with FOIL, x times x is x squared. The outer product is a minus 5x. The inner product is plus 3x, and the last product is a minus 15. Those combine to a negative 2x, which is what we had before I made a mess of this whole thing right here. Okay, sorry, that was a minus 2x. Okay, and that is exactly where we want it to be at this point right here. So what we have in the box is correct. Okay? You guys are probably going to need a whole bunch of practice here at how to kind of recover those skills of factoring. But those two examples are all we're going to take the time to do here today. That's what we call basic quadratic trinomial factoring or reverse FOIL. But now there's two kind of special, we call them special products right here, two patterns that we really want you guys to be able to recognize and then just really kick butt and factor it very, very quickly when you see it. And one of them is one that your Algebra 1 teacher probably tried to teach you and you all just kind of went, yeah, whatever, man. All right, it's really helpful if we get this down. A perfect square trinomial. And the way a perfect square trinomial factors, well, I tell you what, before I get to that, let's talk about what a perfect square trinomial is. Trinomial means that you've got three terms here, which is what we were just dealing with. And a perfect square trinomial is written in this format, which I know isn't going to make a whole lot of sense to you guys right now. It is a squared plus 2 times a times b, and then plus b squared. And I should be careful here. That actually could be a plus or minus the 2ab on that second term. So this right here, everybody, is what we call a perfect square trinomial, or I will abbreviate that as a PST. Now, I don't think at this level we're really, really good at recognizing what that means, so I'll show you that in the context of the next example. But really quickly, what it means is that the first term has to be a perfect square. The last term also has to be a perfect square, and then, this isn't going to make any sense, that middle term is the square root of this term times the square root of this term times 2. Everybody gets that, right? No, but I'll show you that in the next example, and hopefully it'll make a little bit more sense. Now here, everybody, is how a perfect square trinomial factors and why it's called a perfect square trinomial. It factors into a binomial, which is a plus or minus b, close it, and then squared. It's called a perfect square trinomial because it is a single binomial squared that gets you that result. Okay, so I'm going to put a box around this, guys. This is 1000% true, and I want you guys to have this memorized, or at least have it in your notes, but I don't expect it to make any sense right now until we see one or two examples. So let's take a look one at a time right here. Let's do example number 1. X squared plus 12x plus 36. Now, I would totally understand if you guys said, wait a minute, Mr. Fontana, that looks pretty much exactly like, oh, I don't know, this problem, wait a minute, that problem right there. Why don't I just factor this one the same way I did this example, and then I don't have to learn your stupid pattern right here of factoring perfect square trinomials. And you know what? You're right. In fact, that's what you probably did in Algebra 1, and that's why you never bothered to learn this factoring pattern in the box. But I would like it if this time around we saw the connection right there. If you do, it'll actually help you factor some harder expressions here that you might otherwise miss, and I'm going to show you that in a second. So here's what I want to talk about. First of all, what we have here in example 1 is a perfect square trinomial. Let's talk about why. The first term, x squared, is a perfect square. Guys, what is the square root of x squared? X. Then, the last term, 36, is also a perfect square. What is the square root of 36? That would be 6. And now here's the weird part. The middle term is the product of, here we go, this square root, which was x, times this square root, which was 6, and then wait a minute, you remember that weird 2 that was right there? Times 2. X times 6 times 2 makes 12x. So one more time, this is a perfect square trinomial because the first term is a perfect square, the last term is a perfect square, and the middle term is the product of this square root times this square root times 2. Everybody got that? Yeah, okay. All right. And so, wait a minute. What have I done now? Okay, hang on. Redo. All right, let me just erase this, and here we go. Okay, so now that we recognize that this is a perfect square trinomial, we can go back to this factoring pattern right here and say, okay, this is now going to factor into this, a single binomial squared. Okay, so this is going to equal a single binomial squared. I need something here, and a sign in between them. So let me go back a page. What goes here? A, which is the square root of the first term of the trinomial. The square root of x squared is x. Okay, what goes here? B, which is the square root of the last term of the trinomial. What's the square root of 36? 6. And then all that's missing is either a plus sign or a minus sign in between the x and the 6. And whatever sign you were dealing with right here, you're going to use the exact same sign right there. Okay, and so in this case, that sign between the first and second term was a plus, so I'm going to put a plus right there, and this, everybody, x plus 6 quantity squared is our answer. That is the factored form of x squared plus 12x plus 36. Now, if you want to verify that, which I would think you might want to, we could take x plus 6 and square it and multiply it out. But I got to warn you guys, this is maybe the most common mistake that people make in Algebra 2. A lot of people think that this is equal to x squared plus 36. They just distribute that exponent inside there, but that is not right, everybody. It doesn't work out that way. Real quick, if x were equal to 1, x plus 6, 1 plus 6 would be 7, 7 squared would be 49. And over here then, the 1 squared is 1 plus 36 is 37. No, 49 does not equal 37. So that's just a quick counterexample to that line of thinking. Okay, what does it mean to square anything? It means to take the base, x plus 6, and multiply it by itself, x plus 6, and this requires FOIL, everybody. First product, x times x is x squared. Outer product is a plus 6x. Inner product is another plus 6x. The same term happens twice there. And then last product, 6 times 6, is a plus 36. Well, those two 6x's combine to make a plus 12x, and that is exactly the trinomial that we started with. That's how we know that answer is correct. And let's take a look at the second example, which is significantly harder than the first one. All right, guys. Now, I wish I'd done something a little bit different right here. I'm going to remind you, even though sometimes I forget to mention it, the first thing we should look for in any factoring problem is a greatest common factor. And in this one here, we've got 16, 64, and 64. 16 can be pulled out from all three of those numbers. Now, as far as variables, there's nothing we can pull out. The first term has x's but no y's. The last term has y's but no x's. Now the middle term has both, but that's inconsequential. There is no variable, either x or y, that all three of these terms possess. So I'm going to pull out the 16, and dividing it out, that's a 1x squared minus a 4xy squared, and then a plus 4y to the fourth. Okay, so we pulled out a GCF, and now the question is, okay, are we dealing with anything interesting here? Well, what I hope you notice, your first term is a perfect square. Your last term is a perfect square as well. And now here's the fun part. The square root of this is x. The square root of this is a 2y squared. And if we multiply that by 2, x times 2y squared times 2, sure enough, you get 4xy squared. And that tells me that this mess right here is a perfect square trinomial. And once you recognize that, this gets really easy. Here's my final answer, guys. The 16 tags along for the ride, and that's going to get multiplied by a binomial squared. What goes here? The square root of x squared, which is x. What goes here? The square root of 4y to the fourth, which is 2y squared. And then whatever sign you have right here, which in this case is a minus, that goes right there in the middle. And this is what our answer looks like for this problem here. Example 2, everybody. 16 times x minus 2y squared, quantity squared. So that is how you factor a perfect square trinomial. If you, again, just ignored it and just treated it like a regular reverse FOIL problem, I can see why, but it really does benefit you guys long term, especially with tougher problems like this, to learn that factoring pattern. Okay, and the second, and actually the last thing we're going to talk about here, the second special factoring pattern we're going to talk about is something called a difference of squares. Now, a difference of squares, the word difference implies the operation of subtraction. What's unique about a difference of squares, though, guys, is that it is a binomial expression. It only has two terms. So your first term is going to be a perfect square. We'll call that a squared. The second term is going to be a perfect square as well. We'll call that b squared. And because it's a difference of two perfect squares, we put a minus sign in between. So that is what a difference of squares binomial looks like. And that one factors into something really cool. It factors into the product of two binomials. One of them is a plus b, and the other one is a minus b. So I'm going to go ahead and box that up, but now I'm going to introduce just a little bit of vocab. Now, one more time, this binomial right here is called your difference of squares. Okay? Two perfect squares, and they're being subtracted from one another. But this factored expression over here are what we call here two, and here's a vocab word here, guys, two conjugate binomials. Now, that is a phrase I'm not expecting you guys to know already, but we need to learn it here and know it by the time we get out of Chapter 4. Conjugate binomials are two binomials that have first terms that are identical. In fact, I'm going to write that down right here. They have identical first terms, a and a. Whatever this number is here, the exact same number is here. But then when you look at the second terms, this one is a plus b, this one is a minus b. Those are not identical. Those are opposite second terms. And that's what it means for two binomials to be conjugates of one another. Identical first terms, but opposite second terms. And just for fun, let me show you guys that this works. If we were going to try to multiply, let's work backwards to check this now, two conjugate binomials, a plus b times a minus b, well, that's a binomial times a binomial. Let's do FOIL again. First, a times a is a squared. Outer product, a times a minus b, is minus ab. That's all you can do with that with variables. Then your inner product, b times a. That's ba, but in alphabetical order, we usually would write that as plus ab. And then your last product is positive b times negative b. That is a minus b squared. And maybe you notice what happened. Because the outer and the inner products are opposites of one another, they just completely cancel each other out, leaving you with the binomial expression a squared minus b squared. And that's exactly what we were hoping to see. So that's how you factor a difference of squares. And unlike, let me go back a couple of pages here, unlike this factoring pattern for perfect square trinomials that a lot of us tend to ignore and never really learn, and somehow you usually survive, this is one that people usually tend to remember because you have to use it. Let's see it in two examples here. First one's nice and easy, guys. X squared minus 9. Okay, is there a GCF? No. There's nothing you can pull out right here. But what I want you to notice is that this is a binomial, which makes it different than almost every factoring problem we've done so far. These were both trinomials. That was a trinomial. Where was I? This one was a trinomial. But with a binomial, the only way you can factor that is to first pull out a GCF, and second, to look for a difference of squares. There you go. So there is no GCF. Now we have to check, all right, is this thing a difference of squares? So here we go. Is your first term a perfect square? Yes, it is. Is your last term a perfect square? Yes, it is. So this one is going to factor into the product of two conjugate binomials. The first term here is the square root of this term right here. The square root of x squared is x. So I put an x here and an x here. Looking back at my factoring pattern, the first sign is going to be a plus, the second sign is going to be a minus, one of each. And if you wanted to do minus then plus, that's fine too. And then what goes here and here? The square root of this term, and the square root of 9 is 3. Guys, that's it. This one factors into x plus 3 times x minus 3. Okay, can I prove that to you? Let's just show that we're right here. Let's pick a random x value. Let's let x equal something big like 10. Okay, the original value then, guys, x squared minus 9. If x is 10, 10 squared is 100, and 100 minus 9 is going to be 91. What happens if I let x equal 10 down here? 10 plus 3 is 13, and we're going to multiply that now by 10 minus 3, which is 7. And I might have chosen dumb numbers here because I don't think we all have that handy here, but okay, 13 times 7. Let's see if I remember fourth grade math. 7 times 3 is 21. Carry the 2. 7 times 1 is 7, plus 2 is 9. Sure enough, that equals 91 as well. Now, that's just one example. That doesn't really prove it, but I think you guys see my point right there. So that is how this difference of squares factored into x plus 3 times x minus 3. All right, let's move on into this last example here. 45x to the 9th minus 125x cubed. Now, you might be a little concerned here because we set in a difference of squares. The first term and the last term both had to be perfect squares. Well, that's not a perfect square, and neither is that. But I will direct your attention back up here to this little checklist, guys. The first thing we always need to look for, I don't care how simple or how complex the factoring problem is, the first thing we have to look for is a GCF. And what can we divide out from 45 and 125? Looks like a 5 is the biggest thing we can take out. And furthermore, variables. We have 9x's here, we have 3x's here, we can take 3 of those out. So 5x cubed is our GCF. And what's left over now? 45 divided by that 5 is 9. There were 9x's. We pulled 3 of them out. 9x to the 6th is what we get there. Minus 125 divided by 5 is 25. There were 3x's. We pulled all 3 of them out. So there you go. There's no x's left. And now let's take a look, guys. Is that term a perfect square? Some of you might be inclined to say no, but the answer is yes. Here's why. The coefficient 9 is a perfect square, and if your exponent is any even number, it's a perfect square. I'll show you how to deal with that in a second. And 25 is a perfect square as well. So we are not done with this problem. We can keep the 5x cubed out in front, and we have a difference of squares binomial that we can factor. Okay, the square root of 9x cubed. We take the square root of 9, which is 3, and we write that here and here. And now here's the slightly tricky part. The square root of x to the 6th, you're just going to cut that exponent in half. So that's going to be x cubed that goes here and here. So 3x cubed is the square root of 9x squared. The signs are automatically 1 plus and 1 minus, and then we just take the square root of this number here, which is 5, and that goes here and here. And that is your fully factored expression for this difference of squares in example number 2. Okay, guys, that is a wrap. That's everything I've got for you here on section 4.4. I'm hoping a lot of that sounded familiar, although maybe we snuck in some new content right there that you think you were never taught before, and maybe you learned something new then. Okay, so let's give the 4.4 homework a try, and let me know when you guys have any questions. Good luck, everybody.